So in the previous session, as you know, that we started with the discussion of NumPy, and we somehow saw the basics, what a basic code data structure in NumPy is as an ND array, and then we also started discussion how to visualize the NumPy arrays and stuff like that. Today we'll just maybe revise a bit what we have seen. We have seen the first topic was creation of these arrays, how to create these ND arrays. There we saw 6 methods. Okay, the first method was if you have some data types that are in Python, let's suppose some lists, tuples, dictionaries, or something like that, you can just convert them. Okay, and there we saw some examples. That was the first type. Okay, we were in the array creation. So how to basically create these arrays. So in that we saw somehow 6 methods. So just to revise, and I'll just copy paste the code, and because I have written that from the previous session. So if you see the first method, that was when you have any data type, let's suppose lists, and we can convert them into the original data, the original ND array of NumPy. Going to the VS Code, I have already opened that. So now if you see it here, so this is import NumPy as NP. So this is my list. If you see this, this is a 1D list. This is a 2D list. This inside it. This is a 3D list. So that's what I have said: array 1D, array 2D, array 3D. So what I have done is that there is a function np.array. So I use this to convert. Okay, if I just save it and run it, you will see that NumPy arrays are being created. So you can just type the type of these things so that you can also see what is the type. So initially they were lists when you created them, but now if you see that the class is NumPy ND array class. That's the first method. That's the first array creation method. So second method I told you guys is that you can have the. Is there a question? Can you please put yourself on mute? So the second method that we saw is, so I told you in second method there are some intrinsic functions. Okay, some intrinsic functions by the help of which you can create these NumPy arrays. So now in those methods, so documentation broadly classifies them into 1D array creation methods, 2D array creation methods, and 3D array creation methods. So or maybe ND. So they call it ND array creation methods. So there are different methods or different functions which I call. So if you call these functions, so you will be able to create those NumPy arrays. So let's suppose we'll start with some functions which are pretty useful when you will do your data science machine learning. So these functions will be used left, right, and center. So if I again go back to the code window and show you there, the first function we'll talk about, let's suppose I'll comment out this code. First function that we'll talk about is arange. Okay, so the first line that we should write is import NumPy as NP. Okay, and then the first function that we create, arange. Arange basically what it tells you, it gives you a range of numbers. You might have also seen that for loop. In for loop we have that range function, range 0 and to something and step size. Similar is the range function. So let's suppose I want to create an array. Array is equal to np.arange. Okay, and then what I'll do is I'll say give me numbers till 10. If I want to print this, so you can see it is just like the range function. Okay, I'm having the suggestions on, so I should also stop it probably. So let me just stop the suggestions. Yes. So now if you see this, you can see it over here. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the function arange. You will use it many the times. So it has again the same documentation. It has that start, okay, and then it has, after that you can have end, and then there is that step size. Almost similar to that range function that we discussed. Step. So start will, why do you want to start? End means why do you want to end? And end is not inclusive. Okay, start is inclusive, end is not inclusive. By that I mean if you start it from 0, it will take the element of consideration. End is not taken, but end minus 1 element is in the array. And step size is how many steps do you want to jump. So if I just want to create even numbers, so what I can do is I'll just write start from 0 and end till, let's suppose, 10 and step size of 2. So 0 and then jump towards 2 and then again jump towards 4 and something like that. If I print this, so you can see 0, 2, 4, 6, 8, but it did not include 10 because I told you that last element is exclusive. You don't include that in the array. So this is one method. So this arange is a method in which you can create a 1D array. Okay, and the method is linspace. That's again an important method. Okay, just taking this, opening the tab. So here the method that I'll discuss is linspace. So what this linspace does basically is, so in that if you want the elements like this, if you want to have elements from 0 to, let's suppose, 10, but they're equidistant from each other. Okay, they're equidistant. Let's suppose you want the distance to be 1. Okay, and you want these many number of elements. Let's suppose you have 0 to 10 and you want 10 elements, so the separation will be 1 1, so like 0 1 2 3 4 something like this. But if you want elements 20 between 0 to 10, now you know that the distance will be 0.5, so it will be 0 0.5 1 1.5 something like that. That's why this linspace is used for. And when you will plot also, these functions will be really important. So this function is linspace. So what I'll do is array np.linspace. Okay, and then I'll first give from start to the end, and then I'll say how many elements do I want. I'll say I want elements from 1.0 to 4.0, and how many elements I want 6 element, and it will automatically define, okay, do you want 6 elements between 1 and 4, and it will define the distance between that. Okay, basically it'll be 1 to excluding 4, and it will divide that, it wants 6 element, and that will be a distance. So if you now just print it, and you'll get the distance. This is 1 1.6 2.2 2.8 3.4 and 4. Okay, so this is 1 2 3 4 5 and 6 elements. So it has the linspace also includes the last element. Okay, and if you want to see the other functionalities, there you have start, stop, number, endpoint, return step, and you can all read the documentation over here. Okay, this is the I have seen many of the people use it because when they use matplotlib, maybe seaborn or something like that, and they use a lot of this linspace, because you have to draw axes and you want to have equidistant spaces, and these boxes you want to draw. That's why you should know that there exists a function that's called linspace. Any questions still here? Any questions? So we are in the second method. The first was from the data structures that we already have, like lists, tuples, dictionaries, and the second method was the intrinsic functions of Python. So in that we have said that there are three types of arrays that you can construct. The first type is 1D array, second is 2D array, the third is ND arrays. In the first we saw just two methods. We saw a range method and the linspace. These are most frequently used. I'm not giving all the methods. There are a huge number of methods, but these are the most used methods. Any questions still here? I suppose no. Now the second thing that we have is 2D arrays, because we saw some two methods that we are using to construct 1D arrays. Then there is 2D arrays, 2D array creations. So this is under the folder. If you see, we have reached that intrinsic method. So we'll see the famous 2D array creation methods that NumPy provides us. Okay. So the first that there is identity matrix. If you want to create an identity matrix, that we have seen also. So going back to the code window, I'm rushing through it because more or less we have covered all these things. I'm just revising it so that we can start from there. So if you see this, import NumPy, and then I'll just comment out. So if I want an identity matrix, so identity matrix, you will use a lot of algebra in machine learning, data science, and deep learning. So there a lot of times you will need the identity matrix. So what you can do is np.I, and you want to just describe the size. So let's suppose size is 3. And here you can also mention d type, like, and dir, and there are a lot of arguments that you can read about. And please do not remember the syntax. Don't remember the syntax. Even after coding these many years, I still don't remember the syntax, because the thing is, you won't be just coding in one library, but the concepts are crucial. So here you know that there is a method to create identity matrix. So in the PyTorch also there is a method to create this. Okay, in the pandas also you can create something like this, but the concept is that you should have a method where we create the identity matrix. So if you just see this, so this is identity matrix of 3 cross 3. Okay, and this is one of the methods. And then there are other methods also. Like let's suppose you want to create diagonal matrices. So this identity matrix is also a diagonal matrix. So what is diagonal matrix? All the off diagonal elements are 0. So if you see, these are off diagonal elements. So this is called as a main diagonal. So these diagonal elements are having non-zero value. So if you see it over here, okay, so these 1 1 1. So these are diagonal elements. So these are off diagonal elements. So now this is a diagonal matrix, but the identity matrix is that the diagonal elements are only, they have value 1. But if you want them to be having a value other than 1, so what you can do is you can have a let's suppose, and the method that's called as diag. Okay, so diag, or whatever you pronounce it. So I'll call again array is equal to np.diag. This is the method. So first thing is you will give the diagonal element. Let's suppose I want the diagonal elements from 1 2 3. Okay, 1 2 comma 3. Okay, these are the methods, and these are the diagonal elements. And after that, I want it to be 3 cross 3. Okay, and then I'll give this attribute 3. So if you again see it, okay, you see these diagonal elements. So these are the parameters, v array like, and then these k is the optional parameter. Okay, and whatever, and you read the documentation. Okay, and then if I again run it, you can see that this is what got created. Okay, So let's see. This is the matrix that, okay. Again, if you see the 2D matrix, okay, and if you just want a diagonal matrix without this 3, so if you just want 3 cross 3 matrix, that why the diagonal is this. So what you can do is you can have this, okay, without the other argument that I gave, okay. So if you see this, so there is something called as I matrices. So we'll see that those also in algebra, but here you can see that we have different methods of creation of these diagonal matrices. So this is the diagonal matrix that I actually wanted, okay. So 1, 2, 3 is on the diagonal and the off diagonal elements are 0. So this is the method TIAG, okay. And there are other methods also, okay. There are methods like there are something called as Van der Waals matrices. So they are actually used in methods called as least square methods. So there is a function called as Van der, okay. So if I just type this np.vander, there is this function. So right now I am not in a position to tell you what are these used for, but you should know that there are these matrices. If I just have array.np.vander, these are called as Van der Waals matrices. So I'll just give again these numbers 1, 2, 3, 4, and then I'll give the dimension. Let's suppose I'm giving the dimension is equal to 2, say. So if I now print this, you'll see all of these matrices are 2 matrices. And if I give it 3, let's suppose, I'll show you the pattern in there and you will be able to see why it's called least squares. So if you see on these, if you see over here, if you see this, so here you see 1, 1, 1, and then you see 1, 2, 3, 4. Then you see this column is multiplied by 2, 1, 4, 1, 4. Then you see that 1 multiplied by 1, 2 multiplied by 2 is 4, 3 multiplied by 3 is 9, 4 multiplied by, this is squared. Okay, each the element is squared. So if I just increase this, if I just said, let's say I said 4. Okay, now if you see this, so 1, 1, 1, 1. I hope you are you are able to see this. So if you see this, so over here you are having this. This is 1, 1, 1, 1, and then 1, 2, 3, 4, and then again multiply by like square basically. 1 square, 2 square, 3 square. This is again again multiplied by 2. This is 8. 4 2 is 8 and 9 3 27, 16 4 64, and that's why they are called Van der Waals matrices. And I told you that these will be used in generating what are called as least square models. Okay, we'll see what these least square models are, but they are pretty much important. I'm just showing you the important methods which we'll use in our machine learning models and deep learning models. Okay, and then there are these zeros and ones that I also showed you. You can have NP zeros, NP ones. Okay, let me go back to there. So if you see this, so we have an array, and we can call array is equal to np.zeros and give the size. There is zeros like also. If you just want to create a zeros matrix which is likes, which has shape of something, so zeros you can just give the shape 2, 3 or something. So if I just run this, you can see this 2 by 3, all zeros, and you can have ones. Okay, these are all ones, and then you can also, the one more important thing is you can generate random numbers. Okay, for that I would like to have a discussion because previously we didn't see them. So I'm only showing you the methods which I use more or less here and there. I'm not giving you the methods that people rarely use. Maybe sometimes you will create a model, or you will maybe create a program or use a functionality where you will use these methods, but these are the most frequent used methods. Okay, and once you are at that level, once you use the functions that are rarely used by people, at that time I assume that you will be at a good level to understand documentation. I think we have a question. Let's take that. Yes. So in here we'll now discuss the randomness, and after that, after telling you what randomness is and why is it important, and then we'll see what are the methods in NumPy that let us allow this generate this randomness basically. So what is randomness and why is it important? So anything which doesn't have follow a structure, it's called random. So if you ask me what the definition of random, what you can't predict is random. Okay, and let's suppose if there is a process which you can predict, then it no longer remain random. So that's what randomness is. So basically randomness can be thought as in two ways. Pay focus, if we pay attention here. Okay, so the first randomness is that there is some intrinsic randomness, and second thing is the randomness can be lack of knowledge. Okay, let's have a discussion on this first. Okay, what is lack of knowledge randomness? Okay, maybe I should increase the size a bit. It is visible. So what is this lack of knowledge randomness? So let's suppose humans, what they see as random. So if you ask me what is random to me, the random to me is if I haven't seen it, if I can't explain it. Okay, I might have lack of knowledge and I consider it random. Okay, and that's why people try to unveil different things and they say that there is no randomness, it's actually the lack of knowledge. If you see, there is a whole debate between quantum mechanics and classical mechanics between Einstein and Bohr, and because quantum mechanics has something which is called as intrinsic randomness. Okay, and Einstein believed in the randomness, which was lack of knowledge. Okay, if you basically don't know it, that's the reason it seems random to you, but there is an underlying process to that. Okay, so this lack of knowledge and then this randomness basically is we deal the randomness, the whole thing of randomness is dealt in probability theory, while we try to quantify this random. Okay, we don't know the exact method, we have lack of knowledge, and let's create some probabilistic methods which will at least tell us, okay, this is random, I don't know the actual steps, but if I, and there are different approaches also, then frequent test approach, Bayesian approach, we'll see that in probability. But here if you see this, why this randomness is required. So there is a whole field of algorithms called as randomized algorithms. Okay, and if you see cryptography, it's also it is based on this randomness. Okay, and the encryption that you see, that is based on this randomness. There is something called as pure random number generators. Okay, they should generate the random numbers, and these things will be used a lot in cryptography. So that's why we believe that quantum systems can generate pure random number generators. So I'll just give a basic example, so not to dilute the discussion with maybe heavy terms. So let's suppose you want to clean the hard drive. Okay, you have a hard drive like this. Okay, hard drive is basically nothing but there we have a physical representation of a bit, maybe ones and zeros. It may be magnetic bit, it can be flip-flops, howsoever it is. Okay, we don't go to the physical realization. So if you see the hard drive, it's made up of something, and that one unit is a bit, because it can be either in two states. It's called as they are called as binary states, either 1 or 0. Okay, it's a two-step system. So any two-step system, we can use that as a memory. So if you see any video, any file, it is stored as random numbers. It is stored as binary numbers. So 1 0 1 1, something like this. This is the way computer stores it. So you might have even seen that when you delete something. Okay, why does deletion happen instantaneously? The thing is, it does not delete the file. Actually, the deletion might take more time then. So what it does is, it is a reference. So if you delete a file from any modern operating system, so you will see that it deleted in an instant. So what basically happened, it did not delete this. It basically, there was a reference to it. So let's say this was an image and there was a reference to this image. Now it deleted that reference. Okay, when delete the reference, so you somehow lost the access to that data, and somehow this memory was considered free now. So once you again do some operation, so these bits will be overwritten. Okay, that's how you see that there is a free space. Actually, free space is nothing, but it basically means this is not referred by anything. Okay, otherwise memory is never free, because memory there is a bit structure. Okay, but if the structure means nothing to you, okay, see that there are just random bits are there, and if I just read them, it does not make sense. So it is better I'll tell that it is referred by nothing, so it means it's a free space, so I can write over it, and I can have a structured bits now. I can just give 1 0 1 1 0, something like that, and which will create some data, and which makes sense to me. I'll have a reference to that. Okay, and I'll read that. I think we have a question here. Yes. So the thing that we're discussing is that if you see the hard drive, the things are not deleted, just the reference is deleted. Okay, that's why it's easy to recover, because what we'll do is we'll find that header file. We'll see, okay, this header belongs to an image. Okay, and from this to this, maybe this is an image file, and we'll recover those bits and try to give it again the same reference. And once it is opened, and you can see that you can open it as an image. And this is called, so these things basically are, every time you will see the random bits are there. Okay, in the memory, random bits are there. So because it has two states to be in, either 0 or 1. Okay, that means there is data. So what is meaning of the free space then? So free space means if there is no reference to it. Okay, basically we don't refer to it, we call it free space, so you can overwrite onto it. Okay, if you want to actually delete the whole data, so what you should do is, you should have pure random number generators. Okay, pure random number generators, or maybe some random, and you will overwrite these bits. And then it will take the equal amount of time which it takes for pasting the data on the hard drive. Let's suppose you are copying and pasting the data on the hard drive, it takes some time. So if you actually want to overwrite the thing, if you actually want to make this whole drive corrupt, so what you can do is, you have to overwrite all of these bits. Okay, but there still should be the information of what file format it uses. Okay, and there is something called as like boot blocks, and there's a whole structure. This is called as, there's a NTFS, if you have heard about this. Okay, exFAT, these are all file systems. So if you see new technology file system, okay, and this is what the Windows use, and maybe they support all other things also. So this file system tells, okay, why to store those headers, or why to store those different blocks. That should not, this information should not be lost. Otherwise you will have to again create this NTFS, and you will, again, that's the reason you will see, if you have a memory card, let's suppose of 2 GB, that whole 2 GB is not allowed for you. Maybe some MBs are basically kept for this information. Okay, whatever file system, how should we retrieve memory? Okay, that's how you see it. So I was talking about randomness. So this randomness is required. The first information is this. So what you can do is, if you have some random number generators, and you can override these files, maybe you can corrupt some data. And another thing where randomness is used, that there's a whole probability here which deals with it. And there are these algorithms called as randomized algorithms. Okay, and where you take the use of random. And then I said one more application is cryptography. Okay, I'll just give an example of cryptography. So you have to generate two random numbers. Let's suppose if you see your cryptography. So there, your RSA crypto system, which is basically used to encrypt all the data, credit cards, whatever you have. So what it does is, it is based on called as a factoring problem. So it takes two numbers, okay, number 1 and number 2, okay, and it multiplies them together. And there are these numbers are prime numbers, and it's a very big number, and they give a number n3. So to perform the multiplication is really easy. N1 multiply n2, machines can do it very fast, and it gives us n3. But to factorize n3 back into these two prime numbers is difficult problem. Okay. So usually we call this factoring problem is hard. So that's what this whole cryptography is based on. This RSA crypto system said that these are called as one-way functions. So one-way function basically means along one way it is easy to compute. If you see, if I have a function f n1 comma n2, so it will just do n1 multiplied by n2. Okay, but if you take inverse of this function, if you want to invert this, so inversion is really difficult. Okay, that's what factors for. And here you need these random number generators, and there should be some random numbers, n1 generate some random n1, generate random n2, and then multiply them together, and then use this as maybe a key or something, whatever, if you use public crypto system, and then you will see that your whole thing is getting encrypted by using these keys. Okay, and then as I said that if somebody got hold of this n3 also, if somebody is eavesdropping on your connection and they got the hold of this n3, still they won't be able to factor them, because factoring problem is hard, and it is at least now mathematically proven that it comes under the hard problems, and that's why these quantum computers come in. So we have an algorithm in quantum computer that's called as Shor's algorithm. Shor's algorithm said that if we have a quantum computer, okay, and with these many qubits, so we should be able to break this RSA crypto system. So it will be easy to break, and it will be exponentially faster. That breaking will be exponentially faster. Okay, and that's where we use this randomness. We use the randomness in a lot of applications. Okay, it has enormous applications. If you see from probability to this cryptography to these algorithms, it is used everywhere. And sometimes you also need to introduce randomness in your machine learning algorithms. Okay, and for that NumPy also gives us a random module. Okay, and just to answer the Arshan's question, they are not actual random numbers. Okay, there is basically an algorithm behind that. That's why they are called as pseudo random number generators, PRGs. Okay, so there is a algorithm which is behind that, but it looks random to us. Okay, what is the definition of random? So definition of random is if somebody gave me a number 12, so after that what number will come I should not be able to predict. Okay, so I'll give you an example of bit strings. Let's suppose I have a string 1011. So this, if I know this amount of string, so if somebody tells me what follows the next bit, so whatever I guess, there should be 50-50 chance of being true. So that basically means this is pure randomness. I should not be able to predict what comes next. If I even have the history, if I even had these 4 bits, I should not be able to tell what is in the 5th bit, and I should be only able to tell with this much probability, with half and half probability. That is basically means mere guessing. That's what is called as a random thing. Okay, by definition, this is the meaning of random. But if you see in these NumPy modules or maybe PyTorch, they use these called as pseudo random generators. Okay, they look random, but they're not exactly random, and they have an algorithm behind. That's why you see there's a seed yesterday. If you set that seed, let's suppose the seed is set to 100. Okay, and after that, if you generate random numbers, okay, and they'll generate some random numbers based on this seed. Okay, these random numbers are generated by clock time, and different things are taken into consideration. Okay, and that may be one of the tasks for you. How does this random number generators in PyTorch, NumPy, how do they work? But our discussion here is, okay, what NumPy does. I just took a regression so that to give you the clear picture. Why are these random number generators required? So okay, now let's go back to the VS Code and see how are they created in NumPy. So I'll create a new test file, code test6.py. Okay, this is the file. So if you see this, there is a module called as NumPy random. So what we'll do is we'll now import NumPy dot random. Okay, it's inside NumPy. If you see the folder structure, there will be a random folder inside NumPy. Okay, and then what you'll do is you will say import default RNG. Okay, default, pretty bad spellings, default RNG. They're called ring elements basically. So I should write from, that's why it's showing errors. From this I'm importing this. Okay, and then if I want to now create a random number, so what I can do is I can just say default some random number and give me a random. So there is this, so I'll use this now, default RNG, and then I'll say dot random 2,3, give me this size of random number. So if I want to print this, I just directly print it rather than storing. So if you see this, so I'll just run it Python test6.py. So you can see these are random numbers generated. Okay, so I'll just clean it and show you it here. So these are the random number generators. So if I run it again, let's suppose, so you see this like with this like 42 seed element. So if I give 44, okay, if I now see the seed has been changed, so you see this number got changed. Okay, even if I don't give, it should take a random seed. I think this should be optional argument, I hope. Yes, it is an optional thing. Okay, then it will take seed value maybe as time. So you see, if I run this again, you see a different number. If I run this again, you see a different number. But if I fix this seed, if I fix, let's suppose 40, usually people fix 42. So now if I just run it, you will see this is 0.7298 and something like this, again the same thing, because now the seed was fixed. Okay, and that tells you that these things are not purely random, they are pseudo random. Okay, and what you can do is you can again create 3D image. This is the size, and you can read document. Just hover over here in the VS Code, otherwise go to the official document in NumPy, and then you will see this is the whole documentation. And then you will have these default int also, which I think Arshan said. They basically again generate the random number. So from there I'll just maybe comment this out. So I'll say import maybe NumPy as NP. So this is the, and then if I want to generate random number, so what I can do is I want to generate random array. So random, I'll call it array, and then what I can do is np.random. Okay, and np.random dot, now in the random module I'll go at array nd. This is the function. Okay, random is the module, np is the NumPy, random is the module, and then in that I have a function array nd rand. So here you can read the documentation. Random values in a given shape. It will generate random values in a given shape. Okay, and it samples basically from uniform distribution. Okay, between 0 to 1. Let's suppose we'll give you some size 3,2. Let's say. Okay, now if I run this, oops, I think I should directly give the size without being in the tuples. So that's why you should read the documentation. And this also gives the proof that you should not memorize the things. So I should print this, print random array. So if you now see, you can see the random numbers over here. Okay, so if I just run it again, I suppose it should give me different numbers. That is why, because we have not set the seed. Okay, there's a function .np.seed probably. So that is the function np.seed. Okay, I suppose this is, because otherwise we'll have to look it up. Not a problem for us. I think this is not the function. NumPy doesn't have seed, but you will have to look for the seed. You just set the documentation how to set the seed in NumPy, and you can see how to set the seed. And then this number generator basically will generate only the random numbers from this seed, and the output looks the same throughout. So this is one function of random numbers, and if you see, it generated the random numbers from 0 to 1 in the uniform distribution, and we'll see how these distributions are. Okay, but what if you want to generate a random integer, and for that you have a random int, rand int. There's a function rand int. Okay, now it will generate random integers, but we have to give the low and high values. So low high value is till what we want to give the values. Let's suppose I will give low value, because I saw some error here, low greater than high. So what I'll do is I'll give some low values. I want 0, 10, and I want 5 elements of these, something like this. Okay, it is giving the documentation also. You have to memorize basically nothing. So now if you see this, it generated me 5 numbers between 0 and 5, between 0 and 10. Okay, and these are the 5 elements. So if I again run it, I should get something else. Okay, if I again run it, I should get something else. These are random numbers. They look purely random, but they are pseudo random. Okay, now we have a random n also. Okay, so if I will use this random n, so I used rand int. So maybe I'll just write all of these together. So first we use only rand. Okay, and in that we gave the size. So size, let's suppose, was 2 comma 2, something like this, or 2 comma 3. So this is the first, and then we saw random integer. If you want to have random integers, so the first thing is what is the value from which to which do you want, and then how many elements do you want. Okay, then we have this rand n. So okay, in the rand n again, if you read the documentation again, you should be able to go to the documentation. Here, if you see this, you return the sample or samples from standard normal distribution. Again, it gives it from. We'll see what normal distributions are. Okay, now again you will have to give the size. Okay, and if you see these parameters d0, d1 to d2, and the dimensions of returned array, that basically means dimension size, and it returns these elements. I want, let's suppose, 4 by 5. Now if you see this, they'll be again random numbers but without a certain range. So okay, they are just from normal distribution. You see negative numbers, positive numbers, and everything. Okay, but in here you are able to give the integer range. In here you are giving the floating points, and that's how it generates these numbers. So how many of you are able to see how random number generators are now working, at least in the 3 functions we saw so far? And then there is again a choice, so you can choose random numbers. You can, let's suppose you want to choose at random something, so there is a function called as np.choose. So let's suppose what I'll do is I'll create an array. So I'll create my array. This is an array. Okay, and from this sometimes I want to choose randomly something. Okay, I'm saying that choose randomly 3 elements. Okay, and you will see this the importance of this once you go to these permutations, combinations, and in probability. So what you do is basically I'll just write a random sample, and this is random sample, and I'm writing np.random.choice. So this choice is basically telling choose randomly 3 elements from this array. Again, replace basically means false without replacement. So by replacement there are 2 things. You can do it with replacement or without replacement. Let me have a bit of discussion on that also. You might have done these problems in your +1, +2. So let's suppose sometimes you say that I have 2 jar 1 jar, maybe this jar 1 has 2 types of, maybe 3 types of balls. So this is one type of ball, and this is another type of ball, and this is another type of ball. Okay, and then you shuffle them together, you mix them together, and then what you do is you basically take out 3 balls. Okay, you take out 3 balls from this. Okay, and there are now 2 cases. You can have with replacement and without replacement, with and without a replacement. So with replacement basically means you will take 1 ball out, and you will again drop it back into the, you will just see, okay, this color got, and it is pinkish, okay, or it's yellow, or maybe it is purple, and then you will drop it back into the jar. So that's called as with replacement. With replacement basically if you take out the ball and you again drop it back into the jar. Without replacement is you take out the ball, you don't put it back into the jar. That's called as without replacement. And similar is the problem here. So we had an array in here, and we want to choose some numbers at random. Okay, we want to choose some numbers at random. So I'm saying that if you see this function, what I'm saying is this is the array that I generate. 1 2 3 4 5 is the array, and I'm saying np.random.choose. Okay, and this choice basically is choose from this array the size 3 elements. Replacement is false. Okay, do not replace them. Okay, so that I should not be seeing these multiple things. So if I just now run this, so you see that 2 3 5 was sampled. This is called as sampling. Okay, there's a huge problem of sampling, and there is a reverse sampling also. So sampling means this. So when you will be doing sampling, so let's suppose you have a huge amount. Why am I showing you these choosing random examples? And this is a practical implication. When you will do these machine learning algorithms, then you will have data, and in the data, what you will do is you sometimes want to sample randomly. You want to sample some elements. Maybe let's suppose you have these are the elements. Let's say this is your data. Consider this as your data. So this is your data point 1, data point 2 till data point n. So what you want to do is you want to randomly take, let's suppose, some n minus 50 points for training and 50 points for testing. So what you basically do is you don't want to take, okay, I'll take the first n points, first n minus 50, I'll take first, second, third, not like this. You want to just randomize it. You want to say, that's called shuffling. Usually there are in scikit-learn, there are packages where they allow you to shuffle, but I'm showing you one of the ways. So what you can do is you can generate random numbers from this. Okay, let's suppose we have 100 data points. In the 100, what we want to do is we want to have 90 points for training and 10 points for testing. So now there are ways, so you can shuffle this. So you want these 90 points to be randomly sampled. Okay, they should not be sampled one after the other. They should be randomly sampled. Okay, what happens in one of the other, maybe it is sorted and it does not give you more diverse data, so you shuffle it to maintain the diverse data, because the good diverse data, the good quality of data you have, the good model you will have. So what you can do is, so you can generate, you can pick 90 random numbers from this, like let's suppose we have 1 to 100 samples, you can pick at random 90 samples, not by any order. That's where this thing will be useful. So you will have an array maybe of numbers, and maybe these are the indexes of this array. So if this is 1 2 3 4 5, these are 5 samples, and I want to take 3 samples. So what I can do is, so if I just run this, so this is 1 2 3, and now again 5 1 4, you can see it takes it at random 1 3 5, okay, 3 2 5, it continues 3 4 5, it gives you the random numbers. Okay, this is one of the things that why this np dot choice, np dot random dot choice makes sense in data splitting. Okay, there is shuffle also. You can shuffle the array. Okay, if you have this, let's suppose this array, now what you can do is you can say np dot random dot shuffle, and that's what I said right now. Shuffle basically means just change the position. So I'll delete all of these. So why is shuffling important? You probably know. So let's suppose if you are splitting cards, you're playing a cards game, and you want randomness to have that. So what you can do is there a question?
So VS Code is not serving.
Okay. VS Code is not visible. Thank you for telling me this. So I was saying the first thing is random dot choice. Have you seen the choice? I think you saw that choice. In the choice, what we had is, we said choice has it give my array and then give the size and the replacement. Okay, this is what I saw. So I showed you this. Oops. I think I should Python test6.py. Now if you see, these are the random numbers which I chose from these. The first application, I told you that if you want to randomly sample maybe data points from a distribution, or maybe data points from the data set that you have, that is one where you can use this choice. The other thing that I said is, you can shuffle these things. So what is the meaning of shuffling? So shuffle basically means you see each of this is at certain index. 1 is at index 0, 2 is at index 1, then 3 is at index 2, and thing like that. So what I can do is, if I want to shuffle these, so there is a method for that, shuffle it. So again, I was telling you the application of what shuffling is. So if you are playing cards, so you don't want to bias towards any card, so you shuffle the cards. Okay, so as to introduce more randomness. Okay, that's how much important is randomness. If you now see, so this basically gave me random shuffle. It should give me some answer maybe, but it is giving me none. Anyway, you will have to look up the documentation. If I see the documentation, so what it returns none. So this basically actually I think it does it in place. I see. No, it does not do it in place. So you can see it over here. You can read the documentation, and this justifies that I myself don't remember what basically the return or something. So this you will have to see it, because there are so many methods. How many can you remember? So it is better to do it by using the document. You can read a document, modify a sequence in place by shuffling its contents. Okay, and in place basically means, so it does it within the array. So this function only shuffles the array along the first axis, or the order of several is changed, but their contents remain the same. Okay, and it returns this. So if you shuffle, okay, so this should actually get shuffled. But why is it not shuffling? Yeah, it shuffled now. You see, 4 5 1 2 3. That's why I just went to the documentation and see how it shuffles. It shuffles in place. So in place means it does change in the array, original array itself. That's what is the meaning of in place. So this random sample doesn't make sense. It will return none. The shuffle will return none. But what it will do is, it will do it in this in place. So if I just have some more elements, maybe 6 7. So the order is 1 2 3 4 5 6 7. So now if I shuffle this, so you see this order got changed. 6 7 1 3 5 2. It totally shuffled it. Now if you see, it again shuffled it. Okay, it totally shuffles it. It does different permutations. Okay, and shuffle this also will be very important once you do the machine learning algorithm. You will shuffle the data set. You will choose certain number of samples for testing, for training, for validation, and then all these methods that we saw, they are the frequently used methods. Okay, any questions still here? Any questions? So now if you see, so we were studying about array creation. Just to give you again the view. So in the array creation, we said you can have conversions. So by conversions, I mean you can have data types as list, 1D, 2D list, tuples, and dictionaries, where you can convert them into ND arrays. Second thing we said is some intrinsic methods. Some intrinsic methods is there, so which is defined by NumPy. In this, we saw methods how to create 1D array, how to create 2D array, and how to create these ND arrays. and in there we saw different things. We also saw random and stuff like that. And the third method which I said is you can have original arrays. Okay, so you can have arrays, existing arrays. Okay, so what you can do with the arrays, you can either join two arrays, you can mutate the arrays, or maybe you can do some other stuff with the existing arrays, so as to come up with the new arrays. Okay, let's suppose the first thing that you basically do is sometimes you concatenate two arrays, you block these arrays, and these are the methods that I'll show you again. I'll go to VS Code and I'll create a new file, maybe test code test6.7.py, test7.py. I'm only showing you the important method. So now if you already, oops. So what I'm showing you, there are so many methods that also exist for these things. But what I'll do is I'll show you the common method I used, and I think 90% times you'll use these methods. So the first thing is, so now we are at this. We want to have existing arrays, and we want to mutate them, or we want to maybe join these arrays, or we want to do something else so that we make new arrays from the existing arrays. So what I can do is I'll create 4 arrays. I'll create A, B, C, D 4 arrays. And the first array will be array of ones, then identity matrix, and then I'll create identity 0, and then I'll create a diagonal array. So if I just go to the code, and if I show you here, so here if you see I created 4 arrays. So I should import NumPy first, import NumPy as np. So here what I have done, I created 4 arrays. A NumPy 1, so you know it will be 1 1 1 1, size is 2 cross 2, and then identity means 1 0 0 1, and zeros is 0 0 0 0, and then np diagonal. These are 4 arrays which already exist, let's suppose. And what I can do is if I want to join them somehow, there is a method called a block. So what I can do is I can join them. Let's write that result is equal, I'll write np block, np.block. So this is the method. So now what I'll do is I'll block them in a certain way. So how I'll block them? So I basically want them put them together. I want to put AB first and then followed by CD. So what I can do is I can create a 2D matrix. So first A comma B, this will be the first two, and then comma, and then I want to put C and D, C comma D. This is how I blocked them. So if I now print this, print res. So what should I should assume that A should be first and followed by B. So there should be A then B. Okay, then on the below we should have C and D. So this is what we have already had arrays, and we stacked them together somehow. Stacked, or this is called a block, formed a block. So if I now just write Python test7 7.py, you can see this. So this is my A 1 1 1 1. Okay, and then this is 1 0 1 0. This is my identity matrix. So if I want to show this, I need to go here. So here you see this is my A, basically all ones. This is my identity. Okay, and over here this is my all zeros, and this over here is a diagonal matrix of value 3, 4. So I blocked them in this way. So I can block in other ways also possible. So this is one method. This is called as block. So you can join in other ways. Let's suppose I want to vertically stack them, because they are of the same size. So I can vertically stack them. So there is a function called as vstack, vertical stacking. So let's suppose I'll again write result and then np.vstack. Okay, stack vstack, and then I'll give these ABCD. So this ABCD should be given A as a tuple, A comma B comma C comma D. Oops. So B here should be capitalized. That's how I created it. So now if I just print this result, so if you see this, these got vertically stacked. Vertical basically means this. So they got stacked vertically. So initially A. So if you see, this is A. If you see, then this is B, and this is C, and this is called as vertical stacking. So you will require this. You will require to do this vertical stacking a lot in deep learning, a lot in machine learning. So you will have some, let's suppose, data point. You have data point 1, 2, 3, 4, and you want to vertically stack them together. That's why you will use this vstack. And sometimes you want horizontally stack. So this is vertical. This thing over here is vertical, and this is horizontal. If you want a horizontal stack, then there is a function called horizontal stack, hstack. So if I just do that also, so I will just change hstack. Okay, and now if I show you this, so this is hstack. Okay, so hstack, if you see, this is my A. Okay, this is my B, this is my C, this is my T. Basically putting bricks together, something like this. Okay, in here where you are having first, then putting top, then this is, that's why it's called as horizontal stacking, vertical stacking rather, sorry. This is called as vertical. It's vertically going up. If you see this horizontal, this is horizontal stacking, because you are horizontally putting these things together. Okay, and where does it have applications? I told you that sometimes you need to, let's suppose you are performing a deep learning algorithm. You might know that in deep learning we have data batches, so you will take batch of the data and then you will have to put these batches in a certain way so that machine learning algorithm can read it. And if you have data points, so you want to stack them together like this, you want to maybe vertically stack them, and sometimes you want to horizontally stack them. And if you, once we go to these language models and this stuff, and it will be really important to know how these things work. And do not get confused. Sometimes what will happen is, if I write some code, it is easy to convince yourself that I understood this. So better is you write the code yourself and do the assignment with your whole heart so that you understand these things. Otherwise, you will have a hard time understanding the things. Maybe at the top level you say, okay, it vertically stacks, but when you expect the result, you don't know that time. So it is really easy to just, if I type the code and if you see it, it is really easy to convince yourself, why I understood this. But the better part is that you should do it yourself. Okay. So this was the how do we join arrays. We saw methods like blocking, how to create those blocks, and then we saw how to vertically stack, how to horizontally stack. And what you can do is you can also replicate the existing arrays. Okay. So what is the meaning of replication of the arrays? So by replicating array involves basically copying or repeating the elements within the array. Okay. So you have an array, you want to repeat the elements within the array. So what I can do is, so I'll just write the topic area. So you can replicate arrays. There are methods also. So I'm just showing you the most used method. So replicating array. So one method is called as tile. So if I go back, so I have this array, let's say, maybe I should comment out this code. So what I'll do, I'll write an array, and what I'll do is I'll write np dot something, np dot a range. Maybe I'll create a range of maybe till some 3 elements. Okay, so if I just print this, this should be 1 2 3. So print, print, this is array, and if I just save it, go here, you can see this is 0 1 2. I created 3 elements. So what I want to do is I want to replicate certain things. So I want to replicate the array 2 times along the row, okay, and 3 times along the column, something like this. I want to replicate this array, so 2 times along the row and 3 times along the column. Okay, so basically by replicating along the row, I mean, let's suppose if I have this array 0 1 2. Okay, something is happening. So what I'm telling you, let's suppose this is my array. This is 0 1 and 2. So what I want to do is I want to basically take this, okay, this is my array, and replicate it maybe 2 times like this. This is 1, I replicate it like this, and again I replicate, let's suppose I replicate the same thing, and I can replicate it again like this. Okay, replicate it like this, and then replicate it along row wise also. Let's suppose I'll replicate it like this also. Paste, I'll replicate like this. That's why it's called tiling. So you, as if you are just having one thing and you are repeating it multiple times, and you're doing it like this. You're doing it with the same array. Okay, the blocking was different. You are blocking different arrays. Okay, you can also use block here. You can just say a something like this. But here you have a separate method to do this. Okay, if I want to do this, what I can do is there is a method called as tile. Okay, so what I'll do, I'll say replicated repl array, and then I'll say np.tile. So np.tile, which array do you have tile? I'll call the array and tell me the dimensions where you want. Let's suppose we'll call 2 3. This is the tiling dimensions I want to tile in. Okay, then I'll print this. Pretty much basic stuff. So if you see 0 1 2 0 1 2, so here if you see 2 times vertically and 3 times horizontally, that's why this size is 2 3. Okay, 1 2 and 3. This is 1 2 and 3, and you see this has been repeated 2 times. So this is why the size, this is why the tiling is. Okay, and you can use np repeat. So what np repeat is, so then there is again a method np repeat. So np repeat, it repeats certain elements. Let's suppose you want to repeat every element 3 times. So what I can do is I'll just say repeat. I'll say np.repeat. I'll tell you why these are required also. Repeat, sometimes you have to handle with imbalance the data set. So there is a imbalance data set, and what is meaning the imbalance, I'll probably tell you once we reach there. But what you want oversample and undersample. Oversample means you want to take samples multiple times. Okay, that's why this repeat will be helpful there. So let's suppose I want to repeat this. I want to repeat this array, let's suppose 3 times. So now what will happen is each element will be repeated 3 times. If I run this, you can see 0 0 0 1 1 1 2 2 2. Okay, it repeated. Basically, it's called oversampling. So you want oversample something, so you can repeat the data set. So if your data set, and if you want to repeat some data points again and again, so that what you can do is you can just have this method of repeat, and then tell okay what you want to repeat and how many times. Is it clear? and then you can have concatenate two arrays. So we saw how we can block them, how we can stack things together, how we can create tiles, how we can repeat, and then you can also concatenate two arrays. Okay, join basically arrays. I hope that you should be able to do it. And there is something called as column stack, row stack, and all these functions are there. But this add stack, this horizontal stack, vertical stack, and this repeat, tile, and blocking, they are used most of the times. Okay, and but there are also there are a huge number of methods that you can see in the documentation. If you have a certain need, just type it in the NumPy documentation, or maybe type it in the Google. You should be able to get it. But these are the most frequently used. This tile, repeat, most frequently is this h stack and v stack, and probably this block also. Okay, is it clear? Any questions still? I don't assume that you should have question. Yes, yes, you have a question. Give me a sec. Any questions? Yes. Record. So now the concept we will take is resizing and reshaping. That is mutating the data. Okay, I have to repeat because I paused the recording in between. So what is basically the meaning of the mutation is, so you will have something, you'll have data like this 1, 2, 3, 4, and you want to do certain things, and maybe you want to convert it like this 1, 2, and then 3, 4. You want to convert it into 2D array. And I said the applications are enormous. The easy application I said is when you're dealing with machine learning models, there you deal with input separately, so you'll have to reshape the input. So one typical example is when you work with these language models where you have these multiple heads, and each head is attending to certain maybe elements of the data, maybe certain input. So what you do basically is you reshape the data in that way, so that each head is getting the data that is it is supposed to get the data, and that's where this reshaping is very helpful. So now I am creating a new file, code test 8.py. Okay, so this is the file that I created. So I'll show you. Let's suppose if I create an array is equal some np.array range. I'll create a range, and what I'll do is I'll say give me an array of elements. Let's suppose some 25 elements, something like this, 0 to 25. So I should import the NumPy array first. I should import NumPy as np. Then if you see this, if I print, so you can clearly see that as expected results will appear 0 to 24 elements. Oops, so this should be python test 8.py. So now you saw that 0 to 24. Now what if I want 2 by 2? So what I can do is I can say array is equal to array.reshape. So reshape it into the shape maybe 5, 5. But the important thing is, so whatever the reshape element is, it should match this, because a number of rows is this, number of columns is this. So 5 multiplied by 5 is 25. Then only it will be able to reshape. If I do this, you can see it. It is able to reshape. Okay, but what if I said 5, 6 reshape in this? So it should throw me an error, because I want 5 rows, 6 columns. That means 30 elements, but I have only 25 elements. So it should give me an error, obviously. So here you see the error. Can't reshape array of size 25 into 5, 6, because that's not possible. So usually how I use it in my data life. So I'll use this a range. I'll say let's suppose I want elements like 2 multiplied by 3, because if I have test some program 4 multiplied by 5, because this will do this multiplication first. So I want this, and I'll reshape in the same size. I'll say 2 3 4 5. Okay, now if I do this, so you see this is the reshaped version. So now this is a 4-dimensional array of 2 cross 3 cross 4 cross 5. Okay, and I knew this will work. Why? Because I created these many number of elements. This is how I usually do it. So I almost do it daily. So if I have to see, if I'm training a deep learning model and then I'm saying, okay, I should see the batch size. So what I'm doing is I'll open interactive Python on the end, and I'll see, okay, I'll reshape, I'll create this. Okay, how is it reshaping? Because sometimes if you see the reshape, you'll have to take certain elements. So these things come very handy that time. Okay, and you can use 2 into 3 into 4 into 5, these many number of elements. Okay, if I just print this one, if I print the array before reshaping, okay, you will see these 5 factorial number of elements will get created. So this is that. So you got elements from 0 to 119. Now consider this like this. So I want to reshape it like this. Okay, that means let's suppose I have 2 batches. Okay, this is my batch, and this is my, let's suppose sequence length is 3, and this is my, let's suppose number of heads. This is my head dimension. So I have 4. I'm just giving you the reference to what I do on my daily basis. So this is my batch length, say batch length, sequence length. Okay, and then let's suppose this is the head dimension, this is the hidden dimension. Okay, and I have these many, and I have to think of a certain way in which I have to reshape this. So I sometimes use this randomly. I see, okay, these are the elements. So now I have created these 2D arrays out of this. Okay, and then I have stacked these 2D together to form 3D. Then I have stacked 3D together to form a 4D array. So where if you see, these are my 2 batches. So this is my first batch. Okay, and this is my second batch. Okay, and if you see now I have three sequences within each batch. Let's suppose I have, these are my sequences. This is my sequence 1, this is my sequence 2, this is my sequence 3. Okay, and this is again sequence 1, sequence 2, sequence 3 in the second batch. Okay, now what I have 4 heads. Okay, 4 heads basically mean, if I have these, so 4 heads here is 1, 2, 3 and 4 heads. So each of the head will attend to the separate each of these rows. And then I have hidden dimension. Hidden dimension is these columns 1, 2, 3, 4 and 5. Okay, so that's how I use in the language models. That's why you should be really sort of comfortable by reshaping, by knowing the A range and these things, like so that you can interactively use and you can see how do you want to reshape your data so as to get the desired form when you apply let's suppose some algorithm onto it. Okay, and there are again things like np insert, append. You can append the values, you can delete the values, and you can maybe assign certain values. So these are all the methods that are in this mutations. You can resize, you can reshape, you can insert, you can also delete, and you can append. Append basically means insert at the end. Okay, and maybe you can insert anywhere else. There are these methods. So there is np.append. This is the method which also I use, and there is this np insert. These are the methods you can insert, and there is np.delete. You can delete an element. These are all the methods. Oops. So these are the methods. So if you see, documentation should pop up here. You see the documentation. So for this append also there is documentation. For insert there is documentation. Okay, and there are all of these methods. So which these are commonly used methods: reshape, append, insert, delete, and resize also. If you want to resize this. Okay, these are the most common methods which you will probably use in your day-to-day life. Almost 90% of times you will use these methods. Maybe 10% times you will use something else. So coming back, so if you now see, what we have seen so far is we just saw the array creations. So array creation is you can convert, you can have intrinsic methods 1D, 2D, and ND, and you can with the existing arrays, what you can do is you can join existing arrays, as you saw that v stacking, and then you can what I said is you can change values or delete or whatever I said. Okay, in that, and maybe we also read a lot of methods in here. Okay, then I said you can read from disks. As of now we don't have a need, so once we have that need, we'll read from disks. Okay, and then the last thing is creating arrays through these bytes and strings. There's a fifth method, and last method was with the special library with scipy pandas, and these three we'll see once there is a need. But all in all, these methods should be enough for you people to understand, okay, how to create. And there are only 6 methods. I said there are only 6 ways. Okay, only 6 ways are given in the documentation. So 6 ways are there, and 3 of them we saw in the detail, and 4th, 5th, and 6th, they are not that important. They will be important once we start IO. Let's suppose we can read from the files, but as of now we haven't read from the files. But once we use pandas and some other libraries to read the files, there we'll also see how to convert them into NumPy arrays. And then you can also use buffers, and then we can also use special libraries like scipy and this OpenCV to create these arrays. But these are the most important, which probably you will use around more than 80%, if not 90, more than 80% of the times. Okay, is it clear? Now, otherwise we'll move on to the next topic. Is it clear so far how to create these arrays, ND arrays basically? In the previous session, we gave a detailed discussion of how to think about ND arrays. Now, in that we also discussed these 6 methods. Today I showed you most commonly used methods in NumPy or functions in NumPy that we use almost more than 80% of times in your day-to-day life so as to perform the tasks of machine learning and deep learning. Is it clear? Can I move ahead? Or do you want some break? Okay, now before moving on to the next topic, so what you should understand is how are these things stored in the memory. Okay, so I'll show you these. How are these ND arrays? How are these ND arrays stored in the memory? Okay, and this will be really important because in tomorrow's discussion we'll again start it from there, but today I'll introduce them. So let's suppose you have any array. You have these 2D, 3D, howsoever ND arrays you have. You have an array like this array. And then you have, let's suppose, 2D array 1, 2, 3, 4, 5, 6. This is the array. Okay, it's a 2D array. So computer's memory, if you see, it's just a run of bits. If you see, it's a run of bits. It has to store it in run because there is no 2D structure involved in that. So what it does is, so there are 2 orders which how it is stored. So the first thing is called as column major order. Column major order. And another thing is called as row major order. Okay, these are the 2 orders which are used in storing these arrays. So one is called as column major order, and the second is called as row major order. So what is the meaning of row major? So row major order, this is used by C language, and this was used by Fortran, if you know Fortran. Okay, so now if you have to store in the memory, consider this as a memory, because I said memory is run of these bits. So consider this as memory. ये ऐसा memory हमारे पास है. So now what we have is, if you have to store it, if you do it column wise, if you take this column first, so I'll take 1, 2, 3. This is the column. I stored it in column, and then I said I'll take this 4, 5, 6. I stored it like this. This is called as column. This is called as, sorry, row major order. So I took a row. This is row 1, and this is row 2. I took first row, and if you see, I inserted the elements here, and I took second row, I inserted the image here, elements here, and again the third, fourth, fifth, accordingly. So I am taking each row and inserting the memory, and because memory is the run of these bits, and this is called as row major order. This one is called as row major, because I am taking rows and converting them. Okay, and now the second thing is there is column major order. Obviously now you understood that it's 1, 2, 3, and this is 4, 5, 6. It's a 2D matrix. And now what it will do, it will take columns, each column at a time. So it will take this 1, 4 first, 1, 4. Then it will take the second column, 2, 5. It will take 3, 6, 3, 6. Okay, this is how it is stored. It is stored in the column major order. So this is called as column major order in the columns. So now if you, I have already told you. So if you give me the base address, okay, the array, address of the array, so I should be able to go. So there is something, a concept called as stride. Okay, so what is the meaning of stride? I'll tell you that. Now you saw two major orders. You have a column major order and a row major order. Okay, now how does you go on a particular element? There's a calculation that is performed. Okay, now I'll tell you how that calculation is performed. This is 1, 2, and 3. This is 3, 4, and 5. These are the elements. Okay, let's suppose each element takes some b bytes. This is what, how many bytes it takes. Let's suppose the base address. So base address is 100. Let's suppose this is the base address. Now it depends on how you store these things. If you store in the column major order, row major order, if the formulation will change. Let's suppose for the sake of the simplicity, we'll first take column major order. Let's have a row major order, then we'll deal with column major, row major order. So now if the first element it as the 100 location, now you know that it takes b bytes. Okay, let's suppose our memory is byte addressable. By that byte addressable I mean, so we can address each byte. Okay, for one byte there is an address. That's why it's called byte address. There is actually, the word is word addressable. So word addressable means there can be multiple bytes also. So let's, for the sake of simplicity, we say that our memory is byte addressable. That means that each byte is given one address. So that means 100 is one byte, then we'll have 101 byte. So there will be an address to this. 102, this is the address. Okay, if we club 2 bytes together, so we can say 100. This is the address to the 2 bytes memory. And then if we have 101, that means this is 2 bytes, this is again 2 bytes. Okay, so here for the sake of simplicity, I'll say that the memory is byte addressable. So now you know that if it is byte addressable, so this is 100. So what should be this element? So this element, as each element takes b bytes, so this should be 100 plus b. Okay, and this should be 100 plus 2b. Okay, now this should be 100 plus 3b, something like this. 100 plus 4b, 100 plus 5b, because that's how we store it. Is everything clear so far here? Everything clear? I suppose everything is clear. Okay, so now what I'm saying is we have a base address this, and then we have number of bytes. This is number of bytes, maybe I'll say memory taken by each element. And then we have these rows and columns. So now what we have assumed is, we have assumed that this is in the row major order. That means, okay, this is, let's suppose now we have, this is these many number of rows. I'll call R as rows and C as columns. So R is number of rows and C is number of columns. Okay, now what happens if I have to reach, let's suppose, this element, fourth element. Okay, what will happen is basically, so I'll have to have base address first. To base address I'll add something. I'll add basically the number of elements I have to go here. I have to pass 1, 2, 3, 4 elements to reach there. Okay, so I'll just write number of elements in between. Yeah, till number of elements till, let's suppose, this element till that element, whatever it is. I hope you understood this, what I mean by this element till that element. So I am saying howsoever elements came before. So as you know that it is a row major order. Now it is row major, first the row will be stored. Okay, then these elements will be stored. So now what you will do is, you will have which row this is. Okay, this is the 0th row. Okay, then we have the first row, then we have the second row. So you'll have the number of rows that came before it. So if you see the index of this element, if you ask me what's the index, so index is A11. If this is array A, so this is the first. Okay, you have to go to this and then take the first element from there. Okay, so this is my row and this is my column. This is my R and this is my C. That's why I call R and C, row number and column number. Okay, if I have to read this element, so I should come with a formulation because I have to start with a base and these number of elements and then multiplied by the number of bytes B. This is the bytes each element takes. Okay, and I'll reach that location. Now I have to figure out how many elements I have to go through. Okay, now the first thing is I'll have to cross these many rows. If the element was that, I'll have to cross these many rows. So what I'll do is I'll say that row minus 1. This let's suppose if this is at 1, so what I'll do is I'll say I'll have to cross one row. Okay, and then multiplied by how many number of columns are there. Okay, 1, 2 and 3 columns are there, so I'll multiply it with the columns. Okay, number of columns. This is my 1, 2 and 3 columns. Okay, maybe this column should be the total column size. I'll say column dash. So column dash is there, so because I'll have to, so if you see first I'm in this first row, I should get these 3 elements. Okay, and then plus I should add something. So what should I add? I should add how many number of elements are there. So I should add this, basically I should add this one, so the actual column. So these are number of rows. Okay, this should be the formulation. So I'm saying cross these many rows. Okay, and each row has the number of elements. Okay, so what you do is you covered, let's suppose this element was A some 10, 13. So I said first you should cover 10 rows. That means to reach this you should cover the 9 rows first. You should cover these 9 rows. Okay, once you cover these 9 rows, okay, if it's at the 10th row, so that means 0, 1, 2, 3 till, let's suppose this is my 9th row. So till here you should cover these 9 rows. That means number of this you should take this into the consideration. If it is let's suppose A10, that means I think it should be 10. So this is 0 to 9 and this should be 10. So total is 10 rows. So you should take this, if this is R, take this and multiply it with the number of columns. Okay, how many columns are there, because it's stored in row major order. Take these many rows and multiply how many elements are in each row. Okay, that is the column number, how many number of columns. That's how I represent that by C dash. And add to reach, let's suppose this element, this is 13th, let's suppose till here we have 12 elements now. To reach the 13th element we should add this 12 element. That's what I said here. So what you should do is you should do rows and number of multiply by C dash. C dash is the total number of columns, and then maybe C minus 1, because that is the element that we want to get. C minus 1, and if it is 1, maybe C, exactly C, because let's suppose here is only one element because the address is 1, so we start with the C, and we are just subtracting that C minus 1, we are not doing that. So these many number of elements we have to reach, and then multiply by these number of bytes. So this will give you the address. Okay, so how many elements are there? 1, 2, 3. So there we have number of rows previously is 1, multiplied by each row contains 3 elements, and plus before that we have 1 element, and number of bytes let's suppose is B, and the base address is some 100. So 100 and plus 3 plus 1 is 4. So this is plus 4B bytes, so 4B. So this is let's suppose 100 plus 4B. If you see, we'll reach here. So 100, 1B, 2B, 3B and 4B. So this is what the address is. Okay, this is in row major order. So this is the formulation in row major order. I showed you how to arrive at the formulation. So in the row major order, computer does the performing, and we have this base address plus the number of elements multiplied by number of bytes, and you will reach the address. Okay, that's how this row major order works. And I hope that you will be able to also do it the same for column major order. Now in the column, the difference will be, because now we are storing column wise. In order to reach this element, let's suppose this element, you will cross these elements, then you will cross this element. Okay, then you will cross this, and then you will reach here. Okay, if I have a matrix like this, let's suppose I have, this is my matrix. Maybe I'll make it a little bit bigger, and I consider these dots as elements. If I have to reach here, if I have to, let's suppose, reach here, so if it isn't stored in now column major order, column major order basically means you will traverse all these elements, then you will traverse all these elements, then you will traverse these two elements to reach here, and you can come up with the formulation. Okay, as I did it for the row major order. So again, if it is in the column major order, what you will do is you will first traverse here, then traverse here, then traverse here, then reach here. Okay, and now use the difference between column major order and row major order, and that's how in NumPy, why I introduced this in NumPy. Usually you have an attribute called as, there are flags in NumPy, so you can see in which major order it is stored, in which major order is the array stored? Is it stored in column major order? Is it stored in row major order? Why I said you this? Why I told you this? Because when you reshape, actually nothing happens. So nothing basically happens. The only thing that changes is the stride. I'll tell you what stride is. So if you understand this row major order, column major order, and the formulation, nothing will change. Just the stride will change, and accordingly formulation will be adjusted. And then we'll see the concepts of why is it views and copies. What are these? When we reshape, actually we get a view. We don't get a copy. Okay. And if you want to create a copy, you should do that. And after that, we'll go to the indexing. We'll go to indexing, and after that we'll go to slicing also. And I think slicing, indexing, and maybe some other topics we'll handle. Should not take more time, so we should be done. How many of you understand row major order, column major order, and then the formulation changes? Okay, with this I'll close today's session, but tomorrow we'll take a marathon.